In this last video for today, we are going to discuss some of the graph problems. We can represent different like social networks, the World Wide Webs, the road network in the form of graphs. And what I mean by that, like let's say if we are talking about a social network like Facebook, Twitter, or Instagram, something like that, each person can represent a node. And typically, like most applications have that, which is you typically represent a problem in the form of a graph. So in this case, like each person is a node. Let's say this is Jack. Another one is Jill, Joe, and Jason. And these are connected, which is like Jack might be a friend with Jill. So in this case, it's going to be undirected because friendships are mutual in this case. So that's why like both it couldn't be something like Jill is a friend of Jack, but Jack is not a friend of Jill. Like that's not how it works in typically different forms of social networks. In some of them, that might be the case. Like if we take an example of Twitter, it could be like a directed graph because it could be like Jill follows Jack, but Jack doesn't follow Jill, and so on. So uh, for social graphs, social networks, mostly it's unweighted, and some of the questions that might we might ask is like whether Joel is a friend of Jason or not. Or another question that might be of interest for us would be like, let's say if Jack is collect Joel, which is this, I'm terming these like A, B, C, D now. So let's say if A is friends with B and C, but not with D, like there's a lot the feature that's common in various web applications or social networks that you recommend different friends. So typically you want to recommend the friends of friends, which is if A is a friend with B and A is a friend with C, and both B and C are friends with D, it might be a case that your algorithm might be suggesting that A should be friends with D, and so on. So, like, this is a common example. Another one is this idea of World Wide Web. I just discussed it, which is you have each page or each web page as a node, and whether they are pointing to another web page or not as inlinks or outlinks. So, which is if A is a web page like ufl.edu, and I have my website as kapoor.com, I might be pointing to UFL and UFL might be pointing to me, but the probability of UFL pointing to me might be much less. So we can get rid of this one, and so on. So this idea of the World Wide Web you are also going to see in the project 2, which is the PageRank project for the scope of the class. Another one is the maps, which is if you have the map of an entire country and you're using like Google Maps or Apple Maps or something like that. um, Maps are represented usually like weighted, which is if you have two cities or 2 points, there's some weight associated with it, while World Wide Web might not have a weight in that in its case. Also, these are usually undirected. Like in some cases, the maps might be directed, but typically they are undirected, and so on. So, whenever we are solving different graph problems, there are a lot of interesting questions that we might be asking about graphs. One example like that you're going to see a lot is what is the shortest path from S to T, which is if there are two nodes, like we have a huge graph, like let's say we have a really, really large graph. Okay. So one of the questions that might be of interest for us is what is the shortest path between this node and this node? What about like whether the graph has cycles or not? Like that might be another interesting question. And we are going to see like a lot of these questions in stepic problems, or we are going to discuss some of them as like actual algorithms, which is the shortest path we are going to cover like next week, which is there's this famous Dijkstra's shortest path algorithm, which helps you to reach from one node to another. The second one is, are there any cycles, which is again like a very interesting problem. And another one is there a tour that you can take from that uses only one node exactly once, which is if you have a graph like previously we saw some graphs, right, like this. So if you are traversing, is there a possibility that you, like, when you traverse this graph, like just like trees, when we did traversals, we are going to discuss traversals in the next set of videos. But whenever we are traversing, are we encountering the same node more than once or not? The next one is there a tour that uses exactly one edge? Like each edge is used exactly once, which is, if you have a graph like this, you might want to traverse it with just one edge rather than like multiple edges. So in this case, like, you do not want to have repeated edges in your traversals. Now, these are some of the well-known graph problems, and what are their different names. So let's discuss each of them one at a time, which is, the first one is ST path. I just discussed that, which is there a path between vertices S and T? Or if there are two vertices, is there a path between them? And how long is the path? Like, you can calculate that like pretty easily. The second one is connectivity, which is the graph connected? Is there a path between all vertices? Now we are generalizing this problem. Next one is biconnectivity, which is, if we have a graph like this, like let's say we have something like this, and this is extended to a lot of other nodes, and on the right is also extended. Now you see in this graph that this particular node is kind of like a hub node, which is, it is connecting the left half of the graph with the right half. And if we break this, it's going to completely distort all our algorithms, because our vertex is like a critical link. So in a lot of problems, we do not want to have something like this, which is, let's say if we are solving problems related to network connectivity, if we if this server, or if you are representing each server by a node, if this server gets down, it could be a critical point of failure for several algorithms. So we want to make sure, like, if the vertex is removed, will it disconnect the graph somehow? And we want to avoid that. So like, there are algorithms for biconnectivity as well. The next one is shortest SSD path, which is, what is the shortest path? That's again like Dijkstra's algorithm. Cycle detection is another problem, which is, does this graph has any cycles? There are a few questions on stepping on cycle detection as well. The next one is Euler tour. So is there a cycle that uses every edge exactly once? And Hamilton tour is the same problem, but in this case, it is there a cycle that uses every vertex exactly once, instead of uh, just like having edges. So these questions, like on Euler tour and Hamilton tour, some of these questions or some of these problems are too difficult to solve. Like, let's take an example of Euler tour. So Euler tour was solved in 1980s. There's an algorithm that does that. While when we talk about Hamilton tour, it's still unsolved, and there's $1 million prize on solving it. So you have to appreciate the fact that some of these algorithms are really, really complicated. Like, they have solutions, but it's like something like 2 to the power n, or exponential solutions. So we are not going to discuss the exponential ones, but we are going to discuss the most commonly used ones, such as shortest path, or the connectivity and ST path in this course. The next question is planarity, which is whether the graph is a planar graph or not, which is, if you draw the graphs on a piece of paper, will it have any crossing edges? Which is, like, let's say if we have these two nodes, like this is the graph. Now, one way is to have this graph like this, which is, uh, although it's kind of like, I cannot display this in 2D motion, but if you have a 3D kind of, the nodes between the link between these two is going over these two nodes. But a non-planar graph will never have that, which is, there'll always be an intersection between these two, so it's like non-planar or not. And the last one is isomorphic, which is, are these two graphs isomorphic? Which is, like, you might have a graph that looks like this, and another one that looks like this. Like, visually it might look different, but at the end they are representing the same graph. So to check whether two graphs are isomorphic or not, like, that's another common problem. So again, like, these are all like hard problems. We are going to discuss some of them in the course. And in the next set of videos, we are going to discuss, like, we'll start with how we represent graphs in C++, and then we'll move forward to solving each of these problems one at a time. Now, one thing I want to state before we end the video is most of these problems will require a traversal. So just like when we did in trees, like in order, pre-order, and level order traversals, we are going to see like breadth first and depth first traversals and graphs. And almost all of these algorithms will require you to traverse the graph in some way. So our agenda for the upcoming videos is, first we'll represent the graph in C++. Next, we'll talk about the traversals, like how we traverse it. And starting the next week, not this week, we'll start with like discussing some of these problems. That's all for today's lecture. Thank you for joining.